Today we will be discussing mathematical foundations of quantum mechanics. To every quantum system we associate a space of states. A state of a quantum system, or a quantum state, is a vector in this vector space of states. So the space of states is a vector space over the field of complex numbers, and must carry a Hermitian scalar product. So we'll recall what it is. And a state, or a physical state, so quantum state, is not just any vector in this space, but is a unit vector. So this means a vector of length 1 with respect to, this Hermitian form, Hermitian scalar product. The space of quantum states could be either finite dimensional or infinite dimensional. And in this course, our standard space of states, so this will be the space of n qubits, and this space will have dimension 2 to the power n. So it's a complex vector space of this very high dimension. Let us now discuss Hermitian scalar product. So let's start by taking V to be a complex n-dimensional vector space. And suppose we have two vectors in this space. So U is A1, AN with complex components, and V is B1, Bn. On this space, there is the standard dot product. So the dot product on this space can be defined in the same way as it is defined over Rn. So the sum, k goes from 1 to n, ak times bk. So there is a small problem with this definition. So let's take U to be a two-dimensional vector, 1i. What's the dot product of U with itself? So this will be 1 squared plus I squared. But I squared is negative 1. And as a result, we get that the dot product of this vector to itself is equal to 0. And so over Rn, dot product has a nice property that for a non-zero vector, dot product of this vector with itself is positive and is related to the length of this vector. And here what we see is that we have a non-zero vector with the dot product with itself being 0. So this says, for example, that this vector is perpendicular to itself. And so this is something which is not very nice. So there is a way to fix this situation. And we fix this situation by replacing the usual dot product with Hermitian scalar product. So the Hermitian product is defined in this way. So the Hermitian scalar product of u with v is the sum k goes from 1 to n ak bar times bk, where this bar stands for complex conjugation. So if we do this, then in this example, what we get is that the Hermitian product of this vector with itself will be 1 bar times 1 plus I bar times I. And so this is 1, and I bar is negative I times I. And negative I times I is equal to plus 1. So what we get is 2. And now this nice property is restored. So now the Hermitian scalar product is positive, and this vector is no longer perpendicular to itself in Hermitian sense. And we can easily see that the general formula of a Hermitian scalar product of a vector with itself will be the sum k goes from 1 to n ak bar times ak, but this is the sum k goes from 1 to n norm of ak squared. So this is equal to the square of a complex norm of ak. And so what we see, so that it is real, first of all, right? So the Hermitian scalar product of a vector with itself is going to be real and non-negative. Now let us give a formal definition of a Hermitian scalar product. So Hermitian scalar product on a complex vector space V is a product, well, with two arguments, so V cross V, two complex numbers, right? And so what we will denote this Hermitian scalar product using these angular bracket notations, such that it is sesquilinear right? So the standard dot product is bilinear, and sesquilinear means 1.5 linear. So this means that it's no longer exactly bilinear. So this means the following: that 1. So that if we have u with v prime plus v double prime, so this is equal to u v prime plus u v double prime. 2. So the same for the first argument, u prime plus u double prime with v is equal to u prime with v plus u double prime with v. 3. U with lambda v is equal to lambda times uv. And 4. Lambda u with v is equal to lambda bar times uv. So what we see is, so when we say that the product is bilinear, so we mean 4 properties like this one. But the 4th property is not like this for bilinear form. So if something is linear, then you can take out the scalar lambda out of the product. And here, when we take lambda out of the 2nd argument, so it just carries out. But when we take lambda out of the 1st factor, then it comes out with a complex conjugate. So this is where the difference with bilinear products is, and this is why it's only 1.5 linear and not bilinear. Now, so there are additional properties is that, so the Hermitian scalar product has this broken symmetry. So here we have the following property, that Vu is equal to UV bar, right? So this means that it's not exactly symmetric. So when we switch the order of vectors in the product, so we have to take complex conjugation. And so the last property, that it is positive definite. So this means that if U is not equal to 0, then the Hermitian scalar product of U with itself is real and positive. So, and real. So this is the formal definition of a Hermitian scalar product on a complex vector space. And we see that this product here, right, so will satisfy these properties. So it's 1, 2, and 3 will hold, right? And so for property 4, we see that this is because we take conjugation on the 1st factor. Because of this, so when we multiply the 1st factor by lambda, what carries out is lambda bar. And so it's I leave as an exercise to verify this symmetry for the Hermitian scalar product, and the positive definite property we already verified. Now, here we have an example of a Hermitian scalar product on a finite dimensional vector space. Let's give an example of a Hermitian scalar product on an infinite dimensional vector space, which is also relevant to quantum mechanics. So let V be the space of continuous complex valued functions on the interval 0 to L. And so this means that here we have functions from 0 to L, so the argument of the function is real, but the value of the function is allowed to be complex. And then on this vector space, we define the following product. So the product of two functions is defined as the integral from 0 to L f of x bar times g of x dx. And so here, so we take two vectors or two functions, and so this device will produce us a number, and one can easily verify that properties 1, 2, 3, 4 will hold, so it's sesquilinear. Then again, it's easy to verify this skew symmetry, and also, so when we compute the scalar product of a function with itself, what we get is we get integral from 0 to L norm of f of x squared dx. And this is going to be a real positive, right? So if f is not a zero function. Next, let us discuss quantum states for quantum mechanical systems that are particularly relevant for quantum computing. So this will be polarization states of a photon and spin states of an electron. So we're going to see that both of these systems could be considered as physical implementation of a single one qubit. A photon is simultaneously a particle and an electromagnetic wave. So when we have a propagating photon, suppose, so here it flies in z direction here, so it creates an electric field and a magnetic field. And the directions of electric field and magnetic field are perpendicular to the direction of propagation of the photon and also perpendicular to each other. So here we can plot this electric field. So for example, it could be in y-axis, and the magnetic field could oscillate in x-axis. And so this picture will depict a propagation of this electromagnetic wave. From this picture, we see that this wave may have different polarizations. So the same wave that propagates in the same direction along z-axis, we could have that electric field oscillates in y direction, or it could oscillate in x direction, and then magnetic field will oscillate in y direction. So this will describe two different polarizations of electromagnetic wave that both propagate in the same direction z. So suppose a photon propagates in z direction. So we say that it has a vertical polarization if the vector E, so this is the electric component, so electric field component oscillates in y direction. And we say that it has a horizontal polarization if E oscillates in x direction. Now, this gives us two basic states. So we have a vertical state, say, we'll call it like this, so of a photon. So this is with vertical polarization. And we have another state with horizontal polarization. Now, do we have any other polarization states? Of course we do. So, for example, we could have polarization of a wave which is at an angle, right? So, what we could have is, say, if now we represent so this vector as the vertical polarization, right? And this vector as horizontal polarization, then what we could have is we could have another vector which is at an angle alpha to horizontal polarization, right? And so this state psi is going to be a linear combination of these states. So what we say is that the states or quantum states of a photon, they are vectors in the space of states. So this means that we are allowed to take linear combinations of these states. So we can mix these states. And here, so this state psi will be cos alpha times horizontal polarization plus sine alpha times the vertical polarization. So this is another, so this is what's called linearly polarized state. So with angle alpha with horizontal axis. Right, so now, electric field will oscillate in this direction, and the magnetic field will oscillate in perpendicular direction. Now, are these all states, polarization states of a photon? So it turns out that the answer to this question is negative, that there are more states than this. So it turns out that we can create even more vertically polarized states by considering phase shifts. So we could have another wave that is also vertically polarized, but its phase is out of sync with this one, right? And so if so we introduce theta, the phase shift, right? So theta, of course, could be in the interval from 0 to 2 pi. So then, so these new states with the phase shift, they can be written as e to the I theta times the vertically polarized state. So this state will represent a vertically polarized state with a phase shift. Now, physically, so if you have just one single wave, then this phase shift is something that is almost impossible to measure, right? So all physical property of this state will be exactly the same as physical properties of the kind of our basic vertically polarized state. But if you have two waves, so one wave without shift and another wave that has the same polarization, the same frequency, the same direction of propagation, but with a phase shift, then if you have two of these waves, then you can detect that one wave is, has a phase shift with respect to another. So this is based on the phenomenon of interference. So because when you add two waves that have a phase shift, then looking at the amplitude of the resulting signal, you can obtain information about the phase shift. So the extreme case is when phase shift is equal to pi, then these two waves will be in opposite phase. And then when you superimpose two such waves on top of each other, then they will cancel each other. And then the signal will completely disappear. And so this idea of phase shift is behind many physical instruments. And so, for example, so the greatest example is this LIGO detector of gravity waves, so gravitational waves. So how does a LIGO detector looks like? So a LIGO detector is has two tunnels, right, with the beam splitter. So here you put a laser, and then a splitter that sends one beam of a laser in this direction and another along this direction. And here at the ends you have mirrors, and so these two legs of these tunnels are exactly equal to each other in length. And so when these two beams of light travel, then they should come back exactly at the same time, and so they will come back in the same phase. But so this is very precisely calibrated. But imagine now that you have a gravity wave that passes through this detector. So if the gravity wave propagates in this direction, then what it will do, it will make this leg slightly shorter or slightly longer, depending on the phase of the gravity wave. Whereas the other leg will be unaffected, right? So it will just become narrower or wider, but this will not affect the propagation of this beam. And so what will happen is that if you have a gravity wave that passes in a direction which is transversal to one of the legs, then what will happen is that these two beams will return to this point out of phase. And here you have interferometer, and so you can measure the phase shift, relative phase shift of these two beams. And so if your signal becomes out of phase, that when it returns to this point. So this indicates that you have some sort of a wave passing through the leg of your detector. And so if you place several of these detectors at different places on Earth, then if you have simultaneous signal registering in all of them, so this will mean that your wave has cosmic origin, and it's not just a train that passes by near one of these detectors. And so then these waves of cosmic origin that can shrink space are the waves that there's gravitational waves generated by, say, collisions of black holes and catastrophic events like this. Now, let us consider the following superposition of a vertical and horizontal polarization state. I will take a vertical polarization state and add to it a phase-shifted horizontal polarization state, and I will make a phase shift by 90 degrees. So here is the resulting wave, which is depicted. And here I'm plotting only the electric component of this field. So this component has an electric component oscillating in the vertical direction, and this component has electric field oscillating in horizontal direction, but with a 90-degree phase shift. Now, let's see what will be the direction of the electric field component for this composite wave. So here, so at time t equals 0, we see that there is a vertical component to electric field, but there is no horizontal component. So the vector of direction of E is going to be vertical. But then when we move to this point here, so here the vertical component of electric field vanishes, but for this one, so we create a horizontal component of the electric field. So what we see is that the direction of the electric field has rotated from vertical to horizontal. And then it rotates back again. So at this point here, so the horizontal component of electric field will vanish, but we will get a vertical component which goes down. And so what we see is that for this state, so the direction of electric field rotates. And so for this reason, so this is called circular polarization. So this is a circularly polarized state. And so we have, so what is e to the I pi over 2? So e to the I pi over 2, this is simply I. So we have, so this can be written like this, plus I times this. And so there is another state, so where instead of plus I, we can take minus I. So we can have vertical polarization minus I times the horizontal polarization. So both will give us circular polarizations, but different ones. One will be clockwise rotating, and another will be counterclockwise rotating. The phenomenon of light polarization is used in 3D movies. So what's the point of a 3D movie? So we take and shoot a movie not with a single camera, but with two cameras. So these two cameras will represent the two eyes of a person. And so because our stereo vision is obtained through the following means. So our signal that left eye receives is slightly different from our signal that the right eye will receive. And then our brain is capable to segregate the difference between the two signals from the left eye and from the right eye. And so our brain is able to interpret this difference between these two signals as some stereo effect. So we can see things three-dimensional because of this. So then there is no problem of shooting a movie with two cameras that are slightly apart. The problem is then we need to deliver the picture, these two different pictures, to different eyes. So our left eye should receive a picture only from the left camera, and our right eye should only receive the image from the right camera. So this will create 3D effects for the person watching the movie. Now, so this is done using polarized light and polarization filters. So you could have a filter that corresponds, say, to vertical polarization, and this filter will let vertically polarized light pass through it, and it will block horizontally polarized light. So then what you get is, so you can have two projectors that project two movies on the same screen. And the movie from the left camera can be projected with vertical polarization, and the movie from the right camera can be projected on the screen with horizontal polarization. And then you put on the glasses, and these glasses will have, so for one eye, you will have a filter that corresponds to vertical polarization. And for the other eye, you could have a filter that corresponds to horizontal polarization. So in this way, so your left eye will receive only the picture from the left camera, and your right eye will receive the picture only from the right camera. Now, this is not exactly how it works in the movie theater. So the problem with such setup, well, it will work, but then you have to sit really kind of still and keep your eyes straight, because if you decide to turn your head, then so this will be messed up, right? So because now you are supposed to receive the vertically polarized signal, but your alignment of your filter is no longer vertical. And then you are going to get the mixture of two signals, one from the left camera and one from the right camera. And so the image will become blurry. So how to get around this? So to get around this is in 3D movies, instead of using vertically polarized light and horizontally polarized light, they use circular polarization of the light. And so one camera will project the left rotating circular polarization image, and another camera will be projecting with right rotating circular polarization. And then these filters in the glasses, so they are slightly more sophisticated. Instead of having a single layer, so you have two layers. So the first layer will take a right rotating polarization and transform it to vertical polarization, and so left rotating circular polarization will transform into horizontal polarization. And then after this layer, so you put two different layers. So on one eye you put the filter that is only passes, let it pass the vertically polarized light, and for the other eye, the second filter is turned 90 degrees. And so if you tilt your head, then it will not affect the circular polarization, and so now this works much better, right? So I kind of recommend, so after you go to the 3D movie theater next time, right? Well, after all of this is over, and so keep these glasses from 3D movie glasses, and then just get the eyepieces out of them and try to play, so you can superimpose them and rotate and see how, so if you just if you superimpose these two filters in one direction, you can see through, but if you will turn 90 degrees, then all the light will be blocked. So you can play with these filters, so it's quite fun. Now, let us describe the general polarization state of a photon. So this is sometimes called Jones vector. So this general polarization state can be written as, say, A1 e to the I theta 1 times vertical plus A2 e to the I theta 2 times horizontal. Right, so here, so A1 and A2 are positive real numbers. And what they indicate is they indicate the proportion of this mixture. So how heavier is we have this vertical polarization present compared to the horizontal polarization. So these are kind of relative weights. And so theta 1 and theta 2 are the two phase shifts. And so what we see is that really, so what we have here is, so this is just a general form of writing a complex number. So now we can interpret these coefficients as complex numbers. And so this can be written as, say, Z1 times vertical plus Z2 times horizontal. So where Z1 and Z2 are now complex numbers. But of course, so in addition to this, so we need to use some sort of normalization condition. And so the normalization condition should be that this state is a unit vector, right? So this is one of the axioms of quantum mechanics, that physical states are represented by unit vectors. And so then this normalization condition is that, so norm of, or the norm of this state is equal to 1, and this is norm of z1 squared plus norm of z2 squared. So here physical states are linear combination of the two basic states, and the coefficients of these linear combinations are not necessarily real, but complex, right? So if we use real coefficients, then this will correspond to linearly polarized states. But what we see here is that because we can also incorporate phase shifts, so we can create states that are not linearly polarized, right? And then in general, we need to use complex numbers as the coefficients in front of these two basic states. And so we can see that this becomes a possible physical implementation of a qubit. And so here we can interpret as vertically polarized state as 1 and horizontally polarized state as 0. And so this general polarization state of a photon can be taken to be as a qubit. And so it is, in theory, possible to build quantum computers based on photons. Another promising implementation of one qubit is to use not the photons, but electrons and their spin states. So let us discuss spin states of an electron. So here we have two basic states. We have spin up, say in z direction, and spin down, so also in z direction. Well, physicists like to say that one has spin 1/2 and another has spin -1/2. So mathematicians usually say +1 and -1, right? So there is absolutely no difference between 1/2 and 1 in this context mathematically. So these are two basic states, spin states of an electron. And the space of spin states of an electron is a two-dimensional complex vector space so with bases of spin up and spin down. Now, what is a spin of an electron? So it turns out that electron generates a magnetic field, and an electron may be viewed as a little magnet, and so this will indicate the direction of the magnetic field produced by an electron. In an atom, it's advantageous from the point of view of energy for the electron to pair each other, and so on one orbit you will have two electrons, one with spin up and another with the opposite spin. But certain atoms do not have an even number of electrons, and so there will be single electrons that are unmatched in an orbit. And when this happens, then the whole atom will have a spin due to its cloud of electrons. So under normal conditions, so if you have a piece of matter, large piece of matter, so these different atoms will have different orientation of the spins of these unmatched electrons. And so these magnetic fields will average out, and so we don't notice spins of individual electrons in this atom. But so if every atom in this matter has unmatched electron, then by placing this piece of matter in the magnetic field, you can make all unmatched electrons align their spins in the direction of the ambient magnetic field. And then after you remove the magnetic field, then it could happen that your bulky piece of matter will now retain the magnetic properties. So it could happen that all unmatched electrons will stay in the same spin state. And so then what you do is you create a magnet. So this is an instance where you can see quantum mechanics at work. Now at this point you may ask, well, surely we don't just have electrons with spin up in z direction or spin down in z direction. There must be states of an electron where spin goes, for example, in x direction. So where are those states? So how can we write them, and why we don't see them? So the general spin state will be again a linear combination of the two basic ones. So it will be z1 times vertical plus z2 times, vertical down. And so here z1 and z2 will now be complex numbers, and there will be the same normalization, so that the sum of squares of these complex numbers is equal to 1. Now, in order to understand electrons with a horizontal spin, so we need to introduce something which is called Pauli matrices. And so there are three Pauli matrices. So sigma 1 is the matrix 0, 1, 1, 0. Sigma 2 is the matrix 0, minus I, I 0. And sigma 3 is the matrix 1, 0, 0, minus 1. So these Pauli matrices are examples of what in quantum mechanics is called observables. And we're going to talk about observables in detail in our next lecture. But today we are going to just say that, the x-oriented spin states so we can call them spin up in x direction and spin down in x direction. So these are eigenvectors of sigma 1, then y-oriented spin states are eigenvectors of sigma 2, and z-oriented spin states are eigenvectors of sigma 3. Now, for sigma 3, so we see that sigma 3 is diagonal, right? So this means that the eigenvectors are standard basis vectors. And so here they are, right? So these two basic states. So this is the +1 eigenvector for sigma 3. And this is -1 eigenvector for sigma 3. Eigenvectors for sigma 1 are easy to write down. So for example, if we can see that if we take the sum of the two basis vectors, then this will be an eigenvector for sigma 1. So if we take so the first basis vector plus the second basis vector. So then, so this is going to be an eigenvector. So this will be an eigenvector with eigenvalue lambda equals 1. So it's a +1 eigenvector. And maybe to normalize it, so I should put 1 over square root of 2 here and 1 over square root of 2. So in this way, this will become unit vector. And then this is equal to the spin state of an electron, which has spin aligned in x direction, right? And if we take, so instead, the difference, then, so if we multiply this matrix by 1 minus 1, then the result will be, we can see it will be minus 1, 1. So what we see is that this is a -1 eigenvector. And so this will be, again, a spin state which is oriented in x direction, but this -1 eigenvalue tells us that it's a spin down with respect to x-axis. And so what we see is that in this picture we do have states that have spin direction not just in z direction, but in any direction that we actually would want. And but this is just done by taking appropriate linear combinations still of the spin states. And so what we see again, that here we construct a possible physical implementation of a qubit. So we are now, so vertical spin, so this will correspond to the state with where this qubit has value 1, and spin down will correspond to value 0, and then the general state is going to be, so z1 or z0 times 0 plus z1 times 1, and with the same normalization for z values. And so what we get is the spin states of an electron, so they can implement a 1 qubit. So this is what we want. So just as a side note, we can mention that so this idea of a spin is used, for example, in MRI, right? So only in MRI, so we look not at the spin of electrons, but the spins of nuclei of atoms. And so the thing is that for the electron, the space of spins is two-dimensional. So we can have spin plus 1/2, and we can have spin minus 1/2. But now if we take an atom, if we take the nucleus of an atom, which has multiple protons and neutrons sitting inside, then it turns out that spin states of a nucleus of an atom have a larger spectrum. So it's the space of states for the nucleus of an atom is not two-dimensional, but it's finite dimensional, but it depends on the atom, what's the dimension of this space. And the observed values could be not just 1/2 and minus 1/2, but the spin states of a nucleus of an atom could be 3/2 or 2 or 5/2. So it's half integers. And so then the point is that we want to try to understand what is the atom, right? So we want to distinguish atoms of carbon from atoms of magnesium, for example. And we try to do this by looking at their responses, at trying to measure their spins. So how is this done? So we take, say, a patient, right? So that we want to scan. And so this patient is placed inside an extremely powerful magnet. And so then we we hit the patient with a very strong but brief magnetic field. And what this forces nuclei of the atoms to do is, so it forces this nuclei to align all in the direction of this field. And then, so it is so this is not energetically stable state. So after this, so the spins will try to realign, to unmatch each other. And so this will create a radiation response. And then you can detect the radiation that comes from these spin states of atom from flipping. And then by looking at the energy or at the frequency distribution of this response, you can see what were the spin states of the atom after we imposed an external strong magnetic field. And so then you can try to see what is the composition of atoms in your tissue. And in this way, you can get imaging, so you can see what is the tissue variation in the patient. And so this gives us imaging. And so the first, when this technology was developed, so the first name that was proposed was NMR, nuclear magnetic resonance. So here we measure magnetic resonance of nuclei of the atoms. But then, so the public was very scared by this name, because anything nuclear was associated in public's mind with the nuclear decay and nuclear radiation and atomic bombs. And so people were scared of this device because they thought that they're exposed to some nuclear radiation. Although here, this is kind of a far more interesting process. So there is no nuclear fission or fusion that's going on. So here we just measure the spin of the nucleus. And so instead of trying to educate the public, so they just went on PR campaign and called this MRI. So they dropped the word nuclear here, and so now this is magnetic resonance imaging, right? And so, so this is, I find it curious that instead of trying to explain the physics to the public, so they just decided to hide the name and deal with it this way. Now, the next example of the space of states is going to be the case where the space of states is an infinite dimensional vector space. So this example will be not relevant for this particular course on quantum computing, but I thought that I should include this example for your general education. So what we consider here is we trap a particle inside the potential well. So this means that, well, we build walls and we don't allow the particle to leave this space. The space of states here will be the space of wave functions. So these are continuous functions on this interval 0 to L. So psi from 0 to L to complex numbers. And so here we will use the Hermitian scalar product, which is so integral from 0 to L of so psi of x times so this is psi with phi, psi of x times phi of x dx. So this is the Hermitian scalar product on this space. And maybe we should put the condition that because our particle is trapped, so we also impose the condition that psi of 0 and psi of L is equal to 0. So this wave is equal to 0 at the endpoint. Now, how is this related to physics? So here, so we say that quantum mechanics is probabilistic. So the probability of detecting a particle in subinterval from A to B. So this probability is given by the integral from A to B of norm of psi of x squared dx, right? And of course, so physical states have the property that norm of psi is equal to 1. So this means that this is the psi with psi, right? So this interpretation will tell us that the probability of detecting a particle in the interval from 0 to L is equal to 1, right? And then probability of finding a particle from A to B is equal to this integral. And so then this wave function has a meaning of so probability density. Or more precisely, it's the norm of psi of x squared. So this is the density of the probability of detecting a particle in this region. So what are the basic states in this model? So to construct a basis for this space, we can use the Schrödinger equation, which says the following, that a particle with wave function psi has energy E if the following equation holds. So minus h squared over 2m times the second derivative of psi with respect to x is equal to E times psi of x. And so here, so m is the mass of a particle, and h is Planck constant. Now, so basically what we have here is a wave equation. So we can rewrite this equation in the following way. So we can write as d2 psi dx squared is equal to minus lambda squared psi, right? And so here, so this is fairly easy to solve. So here the solutions will be psi will be a times cosine of lambda x plus b times sine of lambda x, Right? But now let us look at our conditions. That's psi of 0 and psi of L is equal to 0. So the condition that psi of 0 is equal to 0, so this forces that A to be 0. So we only have sine functions. And, well, the equation is linear, so now we can drop B. Right? So psi, if we write, so psi is sine of lambda x, then so we have the vanishing condition at the other end. So this tells us that sine of lambda L must be equal to 0. And from here, so this tells us that lambda L must be a multiple of pi. And so this gives us a family of solutions. So where lambda k is equal to pi k over L. But what is lambda in this equation? So we can see that in this equation, lambda squared is equal to 2me over h squared. And so then if we put k here, so then we get that this is equal to pi squared k squared over L squared. And so what we see is that we get particles with a discrete energy spectrum. So we get that Ek is equal to pi squared k squared h squared over 2mL squared. So these are energy levels of these particles, and the corresponding wave functions will be, so psi k of x is sine of lambda kx. So lambda kx, where lambda k is obtained through this formula. So what we see, so this becomes the basis. So these become basic functions. So what we see is that we get an infinite dimensional Hermitian space. So with a basis, and so this basis is actually going to be orthogonal with respect to this Hermitian space. And so then general state here is going to be a superposition or a linear combination of the basic states. And here we come to the well-known mathematical problem of Fourier series. So now a general wave function can be expanded as a Fourier series with respect to these basic functions, these trigonometric sine functions. And we get a description of the general states in terms of Fourier series, and so this Fourier series is in the basis in the basis of functions with wave functions that correspond to a particular energy level. In this lecture, we discussed the states of quantum mechanical systems. Next lecture, we're going to talk about observables and also about evolution of quantum mechanical systems.